Okay, and here we are, third segment of our third lecture of the week. And finally, we can get to the scientific method. It's one thing I wanted to mention before we finish the chapter. Hopefully, we can get through all of it in this segment. I think we can. Because the scientific method is kind of an idea. It's something to keep in mind as you're pursuing science, but it's not really rigidly defined. You can think of it as basically a series of steps where you observe something, you sort of form an idea of why things are the way they are or why it works the way it does, and then you test to see if you were right or not. And if you were right, then you probably try to refine your ideas, come up with more details. And if you were wrong, then you'll have to go back to the drawing board and reformulate. And in science, it's also important to share your results with others so that they can try to replicate your results too. If other people cannot achieve the same results you did, then the results you got were probably the result of some fluke or some particular aspect of your experiment that you may not even be aware of. And that's one of the complicated things about science. There are so many factors that can be at work in causing things to happen the way they do that often factors that we don't consider and are not even aware of will have a decisive effect. And that's why it's necessary to sort of investigate and investigate and investigate and test and test and test, and to have lots of different people doing it in lots of different places under lots of different conditions so that we can be sure that we're really right and that our conclusions are really as universal as possible. We can define the scientific method as kind of you can think of it as sort of a series of loosely defined steps. And these steps involve observation and experimentation. Okay. And lots of measurements too along the way. And the sorry. And the purpose is to basically draw conclusions about why things are the way they are or how things work. Okay. Now, as I said, in order to do this, we have to investigate things very carefully and multiple times because there are often factors that may be involved that we're not aware of. In ancient Greece, they believed that actually reason alone was necessary. And that is in order to figure out the entire world and why things are the way they are, even at the most smallest or technical level, all you really had to do was think about it and reason things out. And while that is an important part of it, I certainly wouldn't deny that reason is a big part of the scientific method. It's not everything. To be fair to the ancient Greeks, reasoning things and thinking about things was about all they were really able to do when you think about the level of technology they had. If you're talking about physical sciences, what kind of measurement devices did they have? What kind of timing devices did they have? I don't think they even had magnifying glasses at that time. So going beyond reason would have been pretty difficult in those days. But anyway, the problem is the most logical or reasonable explanation is often not right. And that's because of unrecognized factors, factors that we're not aware of, or factors that we didn't think were relevant but actually are. So I'll just call them unknown factors. So our goal in the scientific method is generally to come closer and closer and closer to the truth. It's debatable whether the absolute truth on any given matter can ever be fully known by human beings. But our goal, again, like with the scientific method, is to come closer and closer and closer to the truth. In a way, the scientific method actually parallels the way that people or even animals learn. When you think about it, it's just more formalized and rigorous, and hopefully occurs over a shorter period of time than a lot of learning does. But when you think about children learning about things in the world around them, they will naturally make observations. They'll see what happens when certain things occur, and they will form their own conclusions in their head. They may not even be old enough to realize that that's what they're doing, but they'll do it, and then they will test it and see what happens when they do something a little bit different, for instance. And animals do much the same thing at a sort of less sophisticated level, but they form conclusions in a way about why things are the way they are too. And they also form, based on that, they form expectations about what will happen if they do certain things. And that, again, is a very primitive form of the scientific method. The scientific method is certainly not infallible. Scientific investigations have led to various theories over the years, or hypotheses anyway, that turned out to be wrong, or that had to be heavily revised. But that's part of the process. Science is an ever-changing entity, and the scientific method is sort of a continuous development as we try to approach the truth. And the scientific method is actually always open to change. If some aspect of some theory is found to be wrong, then it can be discarded or revised. And then you come up with a modified theory. And then you test that and see if that works any better. And if it does, you keep it. If it doesn't, you throw it out and reformulate again. Anyway, the steps in the scientific method can vary a little bit. Sometimes it varies a little bit depending on which science you're talking about, how things are done. But as I said up here, the steps are kind of loosely defined. But to get the idea anyway, first step would be observation or measurement. Observation is something that the ancient Greeks did. They didn't do a lot of measuring because they didn't have very accurate means of doing measurement. But it's the same idea. And you're observing or measuring some aspect of nature. When I say nature, many people will probably automatically think of biology, because plants and animals. But nature really encompasses everything. Physics and chemistry are ruled by the laws of nature also, and they're part of nature. So you could be observing or measuring some aspect of electricity or mechanics, for that matter, and formulating a theory as to why things are. Some observations may be simple. Some may be difficult, depending on what it is you're observing or how complicated the measurement is. Some may even be accidental. there are, the scientific method is not immune to luck. Sometimes it's good luck. The discovery of penicillin was due largely to an accidental observation. A scientist was working with bacteria cultures, and he was due to go on vacation. And a good, diligent scientist would have cleaned out his petri dishes before going on vacation. But he said, "Oh, to hell with that." And he went on vacation for a couple weeks and came back. When he came back, he noticed that there was mold growing in some of the petri dishes. Fortunately, he was lazy, and instead of cleaning them out immediately and saying, "Oh, that's gross," he looked at the petri dishes first. And what he noticed was, in the areas around where the mold was growing, the bacteria were completely dead. And in the areas where there was no mold, the bacteria were thriving. And this led him to conclude that must be something that's being excreted by the bacteria that's killing off something excreted by the mold that's killing off the bacteria. And that led to one thing and then another, and the next thing we know, we've got penicillin. Because the thing that was being excreted by the mold was penicillin. So that was an accidental observation that led to significant discoveries. Another observation might be, say, measuring the mass of the products of a chemical reaction and comparing it to the mass of the reactants before the chemical reaction, and finding out that they are the same. And you might wonder, oh, does that mean that basically nothing is created or destroyed during a chemical reaction? You might think, oh, wait, when I burn a piece of paper, most of the paper goes away and it's just a little pile of ash left behind. Obviously, something's being destroyed. But if you do that reaction in a closed container, you'll find that the mass of the products after the reaction will be exactly the same as the mass before the reaction. What happens is most of the paper appears to be destroyed because most of it is transformed into products that are invisible gases, like carbon dioxide and water vapor, which normally escape off into the air, and so you don't even notice that that they're being produced. But if you trap the products and weigh them, you'll find that all of the paper is actually there. It's just in a different form. And that led to an observation like that that led to what we now know as the law of conservation of mass. Things are neither created nor destroyed in a chemical reaction. It's just the atoms are rearranged, and the products may look different from the reactants, but all of the same atoms of all of the same elements are still there somewhere. And that all began with the observation that the mass of the products is the same as the mass of the reactants. A series of observations can lead to a hypothesis, which is a tentative explanation from observations. A hypothesis, in order to be a valid hypothesis, it has to be what's known as falsifiable. And what that means is testable. You have to be able to test it and confirm whether it's right or wrong. Or, in other words, subject to confirmation or refutation. Or that it can be proven or disproven. So there are, certain, if the statement is too vague, then you wouldn't be able to test it, and you wouldn't be able to prove whether it's true or not. So it has to be something fairly specific and something that can be tested. And it'll be tested by way of experiments. Experiments are controlled observations often repeated many times under different conditions. Ideally, the hypothesis would be tested by different scientists also, just to make sure that the results weren't the result of some kind of quirk that you happen to be doing as part of your experiment. You lay out, so and this is part of what the scientific literature is all about. If you go looking through a science library sometime, you'll find there are thousands and thousands and thousands of scientific journals out there. And it's very important that research scientists publish their work. Once they form a hypothesis that they think is valid, they'll publish their work giving the details of the experiments and what they think happens and why. And that hypothesis can then be tested by other scientists all over the world. And then those scientists report their results. And hopefully your hypothesis will be confirmed, or maybe it won't be, and then you'll have to reformulate it. Of course, it's possible also that the other scientists trying to replicate your results will make a mistake and fail to replicate your results because they made mistakes. And that's why you want many people to test the results. Okay. If the hypothesis is disproven, that is, multiple other scientists find that they cannot replicate your results, then it has to be either modified or replaced. Or reformulated, as I like to say. Basically, you have to modify it, or completely throw it out and come up with a new one. But of course, that doesn't mean that the new hypothesis is necessarily right. It's probably more right than the first one was, but that new hypothesis has to be tested also. And it may be discovered that parts of that are wrong and have to be reformulated. And so on and so on and so on. Okay. Eventually, many well-proven observations can be formulated into a scientific law. A law in science is a brief statement summarizing past observations and predicting future results. Okay. An example of that is the one I was just talking about. Is the law of conservation of mass. Oh, okay. And that again is the statement that the total mass of products of a chemical reaction, and RXN is an abbreviation for reaction. I use that quite often because it's a word I write a lot. Says the total mass of the products of a chemical reaction are the same as the mass of the reactants. So the mass, total mass of everything anyway involved, does not change during a chemical reaction. You know, that's nice to know, but stated like that, it's of limited utility. What that implies is that matter is neither created nor destroyed during a chemical reaction. And as I was saying before, what a chemical reaction amounts to is you'll have compounds that are made up of atoms chemically bonded together. And during the reaction, those atoms are pulled apart from each other and rearranged and put back together in a different combination. So you get different substances that look different and have different properties from what they had before the reaction, but they're still there. All of the same number of atoms of the same elements are all still there. And so that was a very big and important finding that led just from the observation that total mass anyway, doesn't change during a chemical reaction. And nobody ever has managed to find an example where that's not true. And that's generally true of laws. By the time something is declared a law in science, it's pretty universally accepted and proven to be true. And there are there are definitely no known exceptions to that law. There are some cases, in the case of nuclear reactions, where the mass can change during a nuclear reaction. But nuclear reactions are not the same as chemical reactions. So that's what saved the day on that one. And when you have several well-proven related hypotheses, you can weave those together into a theory. Theories are generally broader and more elaborate than laws. Laws are usually pretty short and sweet, like the law of conservation of mass. You can say that really in just a few words. In fact, a lot of scientific laws, are often so short and concise that you can express them with a mathematical equation, like the one we're going to see for Isaac Newton's second law of motion, which says force is equal to mass times acceleration. There are several different ways that you can say that in words, and some of them are more elaborate than others. Living about 300 years ago, Newton's language was pretty flowery when he described it. Sorry, but you can express that law in just a simple mathematical equation, F equals ma, and that's the law. Okay, so theories, on the other hand, are broader and more detailed and more elaborate than laws are. They act as sort of a model of nature. And they're often able to predict behavior beyond the experiments from which they were derived. So really the mark of a really good theory is not only that it's proven by experiment, and that you don't really have any significant evidence against the tenets of the theory, but also that the theory is able to predict things in the future that haven't happened yet. Okay, so that when things start happening in the future that conform to the theory that you formulated in the past, that's a good sign. An example of that is atomic theory. John Dalton, about 200 years ago, theorized that matter was composed of tiny particles and that they were indestructible and immutable. In other words, you couldn't destroy them and you couldn't change them, which is actually true within the limits of chemistry. Nuclear reactions can destroy atoms and can change atoms from one element into another, but chemical reactions can't. So Dalton, living 200 years ago, he was right about that, actually. And he theorized also that chemical reactions consisted of rearrangements of these particles into new substances, and he was right about that. And that explains the conservation of matter, or conservation of mass. Because the atoms themselves are indestructible. They're still there. They're just in a different arrangement. And theories, of course, are also subject to experimental confirmation and refutation. Since most theories are so broad, though, and so sprawling, it's fairly unusual for any given experiment to refute an entire theory. What'll usually happen is an experiment will refute maybe part of a theory, and that part of the theory may have to be reformulated. And if it directly affects other parts of the theory, then they might have to be reformulated also. But it's fairly rare because before you can really call it a theory, you have to have several well-proven hypotheses we've woven together. It's not very often that the whole thing has to go out the window. And the effect is that that over time, bad ideas are discarded or modified and into better ideas, and we get closer and closer and closer to the truth. And that is really kind of the whole point of science. Another point is that in science, a theory is a very high level of proof, let's say, or a very high level of I don't know, verisimilitude, very high level of reality. If you say to somebody, "Oh, that's just a theory," well, in everyday life, most people, how they would define theory is actually what we in science call a hypothesis. In science, a theory is actually much higher level, or much has been proven much more decisively than a hypothesis. So in science, by the time something is called a theory, it has a great deal of evidence behind it and essentially no evidence against it. So that's kind of the difference between science and everyday life. Okay, well, that is kind of a brief overview of the scientific theory, and that took us a little overtime for this segment of the lecture, so I guess it worked out pretty well. We're only a little over time. See you back in class next week. Until then, goodbye.